Hello guys, how are you doing today? So basically today I'm going to be talking about moment of a force, scalar and vector formulation. And this vector formulation, this moment of a force is more directly related to rigid body equilibrium. During last lecture, basically I was talking about 2D and 3D particle equilibrium. And for particle equilibrium, because of the fact that you are basically doing equilibrium around one point, there is no moment introduced there. Now when you start looking at this as a whole and introducing distances more than a point, now we are talking about moments, and we're talking about rigid body or body equilibrium, which is the next chapter that we're going to be covering. So basically today, once again, it's going to be about moment of a force and scalar and vector formulation. It's going to be like kind of a long lecture, but you know, the lectures are long. It doesn't have to be boring, but they are long. But the important part of this is that you get the theory or the theoretical background for solving the problems, and at least understanding the problems that I solve for you later on. Okay, so today, understand and define moment. This is the same way that I teach in my classes. Understand and define moment, and determine the moment of a force in a 2D case. Now, one of the advices that I give my students all the time is every time that you see a picture, at least in my slides, those are not there only for fun or for any joke or anything like that. I might have pictures also for joking, but in this case, this picture is because he's trying to show you somehow what the moment is about. You have this person here pulling this lever here, which in turn is gonna make rotate that log over there. I don't know. Every time that you see something like that, try to interpret why this picture is here. Why is there any sense? Is there any meaning for that picture to be there? Or for example, this one. What is the effect of this force and this force, those two forces on the wheel, as you are pulling force in one direction and in the other direction? Of course, the whole thing is going to be trying to rotate, and in this particular case, about the only point that can rotate, which is that one. Another application, what is the effect of this force here on that lug nut over there? Once again, you know, you have a force, you have application of a force, you have a point, you have a distance. Kind of that is showing you important features of moment. So what is moment? And I always say this, what do you remember about moment? Wait a moment. And somebody, of course, wants to be funny and say, oh, moment is a brief instant or brief period of time. Yeah, never heard that before, so don't say that. So words that are related to moment, because I know I'm pretty sure that before today you heard about moment and you heard about something related to moment. And usually words related to moments are torque, moment, torque. Are they different? Are they same? We can discuss that later on. But yes, definitely torque and moment are somehow connected. Twist. Now twist is twist in this way. Well, twist is also related to torque and to moment. Force. Well, in every single one of the pictures that we saw before, you could see forces and application of forces in points. So yes, rotation. Rotation is very important, because basically rotation is telling you that when you apply the force, some rotation about certain point is happening. And then there are people that remember that torque was cross product, was related somehow cross product, and yes, is somehow related. Or bending in this way, bending, because you have twist or torque in this way, and then you have bending in this other way, or bending also in that way towards you. Those are bending. What else? Force times distance, which, well, force times distance or force cross distance or distance cross force is also coming from here and coming from here. Yeah, everything that is there has to do with moment. So what is the definition of moment? If I ask you what is the definition of moment, probably you're going to tell me force times distance or distance times force. And that's not the definition of moment, but that is the equation, or that's the way you calculate moment. So I like to come out with my own definition, and usually I try my students to come with their own definition. And I say, let's imagine, I like to play mental games and experiments all the time, so let's imagine that is a file cabinet, a file, a real file, like not the one that I have here in my bag over there. That's a file cabinet, imagine, not the virtual digital cloud cabinets that you know. So yeah, guys, those cabinets exist. That's a part of history, but yes, they still exist. So imagine this is a cabinet, and somehow this is you, and you are trying to push that cabinet here. Well, if I push that cabinet at a certain point somewhere there, I know that cabinet is gonna move and it's gonna slide. And try to bear with me here. There is a bunch of incongruences in this example, like friction, where the friction is applied, equally distributed weight. But you know, bear with me. Let's neglect that type of situations, and let's see what happens. Now, instead of pushing it there, let's say that you're pushing it here higher. What do you think is going to happen if I push it higher? Well, if I push it higher, that thing is going to try to tip over. I'm not saying how high or how strong, but it might tip over, but it might also slide. Those effects can happen there. Now, what happens if I now push it in that direction? Well, it's going to try to tip over in the other way, and it might slide also in that direction. Now, what happens if some of you I know that might be thinking of doing that now? What happens now if I push it really lower here and really hard with a really big strength over there? Well, then that moment or that effect, that rotational moment is going to be bigger, and something like that could happen, and that could be you at the end of the experiment. I know, just saying. So what have we learned so far? If you study that experiment, that easy experiment that we just did, what we learned is that there's going to be a point that when you apply a force at that point, or with respect to that axis, for example, there's not going to be any rotation whatsoever. It's just going to be translation from one end to the other end. Now, I know also, and we show, and it's something intuitive, that if we move a distance d from that point, I don't know what that point is once again. Well, I do know what that point is. I just don't want you to know it so far. So, but if I move from that point farther away from that point, we're going to have that rotation or tendency to rotate, and also we can have translation. Now, if I make that distance bigger, of course that rotational effect is going to be also bigger. And if I go in the other direction, then we're going to have the rotation happening in the other direction also. So what have we learned so far? That cabinets are heavy and you need a hand truck? No. Well, maybe you learned that also, but what we learned so far is that the moment, or that rotational effect, which is the moment, is directly proportional to the distance. To the distance with respect to what? To that point in particular, to one point in particular, or to one axis in particular. Now, keeping with the same order of ideas, imagine that you have the same cabinet and you have that force, and you apply the force at a distance d, then you're going to have that rotation. We discussed that before. Now, what happens if I keep the same distance but I increase the value of that force? Of course, that rotation is going to be bigger also. And that means also that the moment is directly proportional to the force. And everything that we're talking about, it is in the linear analysis. You are not at the non-linearity yet, so forget about it. In the linear analysis, moment is directly proportional to the applied force. So what is the definition of moment then? Remember what I said? There is a point involved, there is a force involved, there is a distance involved, and there is a rotational effect involved. So moment, if you want to define moment, simple, the moment of a force, this is the way it's called, moment of a force is a measure of its tendency to cause the body to rotate about a specific point or axis, if the force and the axis are not in the same point, which is what happened, you know, when you have the cabinet and I have the cabinet here and apply the force and then only slide. That what happened, because the force and the line of action wasn't the same. The point and the force line of action was the same point. And then you have some examples of moment application over there. And yes, moment is calculated at force times distance, but we have to talk a little bit better of what force and what distance R in this case. So moment of a force, scalar formulation, give me a lever long enough and a place to stand and I can move the earth. Who said that? 5, 4, 3, 2, 1. So sometimes I get confused with what finger I take. 1, 0. Who said that? Archimedes. Yes. And Archimedes said that this is the time frame where Archimedes lived. And I was in one of my classes and I asked, oh, Archimedes, you know Archimedes, right? I said, yes, I know Archimedes. Who was Archimedes? The owl on the sword and the stone. You know that little owl there? That's called Archimedes, but no, this is not the Archimedes that we are referring to. Archimedes is Archimedes of Syracuse. And you know, I was a Greek mathematician, scientist, the Archimedes screw also. You remember Eureka? You remember that crown thing, the problem, physics, crown made out of gold, gold plus silver. And he was commissioned of seeing if the crown had silver on it, and they were trying to cheat the king, which was an error because they were probably gonna be beheaded. And he came with the solution at the end, and by submerging the crown in water. And it came apparently when he was taking a shower or taking not a shower, please, taking a bath, and he saw the volume of the water being displaced by his volume, his own volume, and in that way he could come with a calculation of that and determining that the crown actually had silver on it. And I don't know if the guys were beheaded or not. This is just me speculating. Okay. What happened here? I don't know what happened there, but that shouldn't be happening there because we were still here. No, this is not it. Oh my God, what happened here? What happened with that? Don't move. Here. Oh, because I was here and the smart guy, instead of pushing this, he clicked enter. And now I have to go by hand back. Forget it. Forget it. Forget it. Forget it. Forget it. Forget it. Archimedes. Archimedes. Here is Archimedes. So I was here in this part, and I was supposed to. Let me go back here. Let me go back here. I'm sorry, guys. This is live, so I'm not gonna edit it. Here. And now I don't see myself. There you go. I was supposed to do this, and I was supposed to do that to go back. So difficult, right? Well, anyway, yeah, that was Archimedes. So, and if we're studying moment of a force, scalar formulation, and we are working in 2D. And if you see this from the top, basically, let me go back here. You see, this is the leverage. This is the point. So this is the rotation that is happening about that point, and that's why this picture was here. Archimedes, you have a force here and a distance, and of course the bigger the distance, the bigger that rotation is gonna be, and the force could be smaller. In this case, the distance here is smaller, and it can lift a really heavy force, just because you have a ratio between this force and this distance, and this force and that distance. Well, anyway, so if we are studying what happened here, for example, this is a hand here pushing this wrench and for unscrewing that pipe, and we see that from the top. Basically, this is what we are seeing. The magnitude of the moment in 2D, the magnitude, once again, of the moment in 2D is that force times that distance from the point that you want to calculate the moment. And this is the rotational effect here. Notice that that distance and that force is perpendicular. So in order for you to calculate this in 2D, not using vectors, not using anything else, just a simple multiplication of the magnitude of the force and the magnitude of the distance, that force and that distance should be perpendicular. And it is important for you to repeat this. D is also called the arm, and that arm is the in 2D it doesn't affect you that much, but when we go to 3D aspect, which is the next chapter or the next lecture, it's going to be very important that you say it in that way. That arm or that R is, don't say radius first at all, it's not radius. That arm is the distance from the point to the force or to the line of action of the force. From to, not from to. From the point to the force or to the line of action of the force. If we are not using vector, it has to be perpendicular. So does that mean that if this is not perpendicular, then you don't have any moment? No, that's not what it means, because how are you going to ensure that this is perpendicular to that one? So then if I push it a little bit slanted like that, that means that it's not going to be, there's not going to be any moment there. No, that's not what it says. But if this is not perpendicular to this, only the perpendicular component is the one that is producing rotation, because the horizontal, the component that goes through the axis, in this case, that will try to push in one direction or the other, so meaning translation, not rotation. Okay, so arm is the distance from the point to the line of action or to the force, perpendicular, and the direction of the moment in 2D is just expressed as clockwise or counterclockwise all the time. You can use positive or negative if you say it beforehand and say clockwise, positive, counterclockwise, negative, or vice versa, whatever convention you want to, but you say clockwise or counterclockwise. That's the direction that you say to the moment. And what are the units of moments? Once again, 5, 4, 3, 2, 1. Look, force times distance. So unit of force multiplied by unit of distance. Unit of force times unit of distance. Unit of force times unit of distance. That's going to be the moment, which, if you remember, is also torque. So what is the difference so far between what we call now moment and what you call before torque? Moment, bending moment, torque through the axis. That's the only difference in reality. Okay, any questions so far? Of course not, because I will be asking questions to myself. You can ask questions, but I'm not gonna listen to them so far. So let's do an example. And the example that I want you to do is this, and it's a very simple example because it's the first one, and it says you have a 400 Newton force applied there at 20 degrees in this, it looks like a gallows thing, I don't know, in that structure. And we have to calculate the moment of the force with respect to the point A. Why with respect to the point A? No reason in particular. There are reasons, of course. There are reasons for that. And there are very important reasons, like this is the point where this is joined to the ground, and probably you have to detect the failure there. But in this particular case, why the point A? Because the problem is asking you to calculate the moment with respect to the point A. Plain and simple. That's it. And I'm going to solve this problem in 3 different ways. The really long way, which you should avoid, unless it's the only one that you know how to. Hopefully you're going to know how to do it differently after today's lecture. The not so long, street smart way, and the way that you should do it. Because when with one force, it doesn't matter too much what you do. But when you have 5, 6, 7 forces, the third method that I'm going to explain you is going to be the best method. So let's start with the really long way to do that. And I do it like that on purpose, so you realize that you can do it using geometry. Because the only thing that I know is what is moment? Moment is a tendency to rotate with respect to one point, in this case the point A. And then I need to find a distance that is going to be perpendicular to the line of action of the force. So basically, if that is moment, force times distance, I need that the line of action of this force, I need to find this distance d. That's what I need to, basically. And all my problem is finding that distance d, because I know the force is 400, and I have the geometry here that is going to allow me to calculate that. Now, it is a little bit of work, but yes, you can do it. I cannot find this distance directly, but I know that the total distance is 3, so I can say this is L3 and this is L4, and then I can say that this is L1 here and this is L2. So if I add L1 and L2, I'm gonna have D. So how can we do that? Well, let's start with the triangles, and let's start with this triangle here. If I have that, once I find that D, I just multiply that D times 400, and that's it, problem solved. Now if I start with this triangle here, I know how much is this angle, and that angle is 70. Very well, well said. And how do you know that is 70? Well, because you know the sum of all the internal angles of the triangle is 180. So yes, that is 70. Really, there's nothing else that I can do with the triangle so far. So, but I can go to this other triangle here, and I know this angle is also 70. Yes. Why? Because these two are called vertical angles, or opposed by the vertex angle. So this is also 70 degrees here. But here I can calculate L4 and I calculate L2 because I know this distance here too. So if I know this distance here too, then this angle I can calculate it also, because this is 90 degrees, 90, 70, that means that angle is 20 over there. And then I can calculate L2. L2 is going to be equal to 2 divided by cosine of 20, or I can use 70 for that also and use the sine. But I can calculate L2 in that way. So basically I have this part, I only need L1. Now L1, from L2 I can't calculate it, but I can calculate this L4 here, and that L4 is going to be 2 times tangent of 20 degrees here. So I have L4, and then I have the total distance, and the total distance is 3. So L3 could be 3 minus L4. I can do that. And once I have L3, now I can calculate L1, because I know this angle here 20 also, and I say that L1 is the value of L3 multiplied by sine 20, and I get L1, and then I add L1 plus L2, and I get my D. And once I get that D, the only thing that is rest here to do is multiply that D times that force and get moment. That's it. It's not difficult, but it's long. And if you have several forces, it's going to be longer. So try to avoid that if it's possible. Now, when it's not possible, when you don't know anything else, when you don't know any better. Now, the only thing that we haven't mentioned here is the direction. Well, in this case, it's obvious, right, that this is rotating in this way, and that way is counterclockwise. First method, solve. Kind of laborious method, because look at all the calculations, all the things, all the knowledge involved. With previous knowledge, you know it. But let's go to the second method. Moment is the tendency to rotate of a force with respect to a point. And the point, what I have to calculate is that the distance and the force have to be perpendicular, but nobody tells me that the distance should be perpendicular to the force. I can maybe find the force perpendicular to the distance if that is easier to me, and that's the second method. There is a very easy way that I can calculate this distance, but wait, this distance is not perpendicular to that force. But this distance is really easy to calculate, because it's just the square root of 2 squared and 3 squared, and I have that distance. Now, if I multiply this times that, that's not going to be the correct effect, because that force will be slanted with respect to that distance. But I can find the perpendicular component of that force with respect to this distance. And also I'm going to have a horizontal component here, an axial component. But the axial component is passing through the point, and it's just trying to push it, not to rotate. So the one that I'm really interested is in finding this component. In order to find that component, I know this angle is 20, but I don't know this other angle here, this other angle alpha. Can you calculate this angle alpha? Of course, you have this distance 2, you have this distance 3, and that alpha, you can say that is the inverse tangent of 2 divided by 3. Calculated that angle alpha. Now, my total angle from the force to the line is 20 plus 33.69. And if I want to find the perpendicular component, this one, I'm pointing at this one because this is this, but remember it's applied here. So this perpendicular distance is just 400 multiplied by sine of this whole angle here, which is this. And this is the perpendicular component of the force with the distance. Now if I get this, this value and I multiply that value times that distance, that's gonna give me my moment. And that's gonna be also in the location that we said before, counterclockwise. And it's the same value. But look at the only math involved, it's really short. So that's not that bad unless you have to do the same analysis and try to find, I don't know, 6 forces, because the problems that we are solving are kind of like that. It's never going to be only one force. So now I'm going to show you the method that I want you to do it, because in my opinion is the easiest possible method. It's a standardization of this method basically. So how are we going to do that? We are gonna resolve like the same way that we said before, when you have Cartesian, etc., etc., etc. We're gonna do the same thing now for x and y. So we're gonna resolve every one of the forces and find the perpendicular and horizontal components, or x and y, and we're gonna calculate the moment using scalar analysis. Okay, how this thing works? This thing works like that. This is the problem that we have to solve. So I want you to really do what I'm telling you to do. First of all, I want you to imagine that that frame over there is not drawn in the paper, it's built on top of the paper. And once it's built on top of the paper, basically I get rid of the paper. I don't want the paper anymore. And whatever is the point that you want to calculate the moment, imagine that you're going to put a nail in that point. Okay? What does that mean by a nail? Let me see. Thumbtack. I'm looking for a thumbtack because I prepared something. Let me change this really quick here. Better say. There you go. Yeah, I built this little thing right now. I just put a staple there. And this is the thumbtack that I was desperately looking for in my drawer. So if I put a thumbtack here, that's what I did there. Imagine this is the point A. Basically, what I'm doing, I don't want to push this too hard because last time I pierced my desk. But let's say there. Okay. Basically, if I put that thing over there, that is free to rotate with respect to that point. That's rotation. What is that? Moment, tendency to rotate. So basically that's what we are putting that nail over there. Got that part? Okay, good. And if you didn't get it, you didn't tell me, so I didn't hear you. Okay, now this part here. Now the second part of this procedure, once you imagine you had that, actually I put my finger there in the paper and I tried to move it with my hand, even though it's not built on top of the paper. That's what I imagine. I move the paper. So I'm gonna get the force, this force that is applied here, over there, and I'm gonna do something that is, I'm gonna decompose that force in horizontal and vertical component, because those are the two forces. If this angle here is 20, as we said before, the vertical component is 400 sine 20, and this is 400 cosine 20. And then we are going to apply something, well, I put my axis of reference there just for easiness. And then we're going to apply something that is called superposition principle, or it's called also Varignon principle. Varignon, I don't know, I know you know who Varignon is, because you have a bunch of reading nowadays. Yeah, unless it's a video game that is called like that, it's very difficult. But Varignon was a mathematician, actually. He's a French mathematician, and he has several cool theorems, and one of the theorem is this one, superposition principle. But Varignon has another one that is really cool. You should check it just for curiosity, because it has to do with quadrilaterals in any shape. And if you go to the center of the quadrilateral and you form another quadrilateral, and the area of that quadrilateral is related to the main one, but I don't want to go in there right now. So anyway, basically what Varignon principle or superposition principle is, which is, by the way, really powerful principle in engineering, that principle says that it's like divide and conquer, but backwards. Why? Because it says that if you have a bunch of forces and moments applied in a particular rigid body, the total effect of all of those is the same thing as if I apply one by one and I calculate the effect of one by one, all of them individually, and I add those effects. So in this case, we have two forces. So instead of having the two forces, I'm going to study the effect of every one of those forces by separate, and then I'm going to add the result. That's that simple as it is one of the most powerful things that you can have, because it applies basically to every linear structure. So what we're gonna do, we're gonna study the effect of the first force. And if I go back here to my little thing that I did here, it's like having this here and applying the force in this way. So if I apply the force here, this is gonna happen, but we're gonna see that later. Okay, just keep that in mind. So basically I'm gonna study that force, and we're gonna say that moment is just force times distance. So I'm gonna calculate that effect, and I'm assuming, just for the sake of adding or subtracting, I'm assuming that everything that goes counterclockwise, I'm gonna say that is positive. Clockwise will be negative. So force times distance, right? What is the force? The force is 400 sine of 20. But this is the key. If the force is vertical, the distance has to be horizontal. In other words, I don't have to calculate any distance, because usually you have all of those distances. Perpendicular distances, horizontal distance, vertical distances. You have all those distances. So that step of calculating the perpendicular distance, basically we're solving it by decomposing the force. So if the force is vertical, the distance has to be horizontal. The force is 400 multiplied by the horizontal distance. What is the horizontal distance between this force and that point A? Horizontal distance, this distance. That distance is 2. Oh, it says here 3. So I put 2 here. Oh my god, you got me. There's an error there. Kidding. 3. It's just to see if you were paying attention. That's it. So 3. You have these 3 here. Now that's the horizontal distance associated with this vertical force. 3. Now, after I have that, I do something that is I call studying the sign. And by studying the sign, is exactly what I told you before. I said everything that rotates in this way, meaning counterclockwise, is going to be positive. So now if you're going to study the sign here and you apply this, look how that is rotating. That is rotating following this. And that is what? Counterclockwise. And counterclockwise to me is what? Positive. Even if you don't have this and you just draw it in your paper like that, you can put your finger there and you can apply the force here. And by applying the force there, you move the paper completely like that. You see, you don't have to build it, but you have to imagine that it's built. So then it's counterclockwise, and we say counterclockwise is positive. So once again, if you apply that force over there, this is what is going to happen. And that is this direction, and that direction is positive according to our convention, and that's it, positive. Good. Now we study the other force, and we go back and we say, okay, superposition principle. This is the effect of the perpendicular or the vertical component. Now I'm going to study the effect of the horizontal component. That component over there. And that component was 400 cosine of the angle. So what we're going to do, we're going to pull it in that way. And here, you know, sometimes, and I'm going to go back, well, let's keep going, and then when we study the sign, oh, I'm sorry, I will make that comment to you. Now, some students, including me, when I was taking this class some centuries ago, have issues when the situation is like that, because some students, some of you don't have that issue, but some students have that issue, that when I pull it here, it looks like they could be doing this or it could be doing this. So in this way or in this way. If you are one of those, and if you are not also, because in some other complicated cases you can use that, once again you apply another thing that I'm going to show you, another trick that I'm going to show you now. So that force is how? Horizontal. If the force is horizontal and this is the value, I need the distance. So if the force is horizontal, how the distance should be? Vertical. Very good. So if the force is horizontal, the distance should be vertical. And the vertical distance between this force and the point A is this. And that distance is 2 meters, so I multiply that by 2 meters. Now, clockwise or counterclockwise, if you have that problem, we're going to use another principle when we study design that is called the principle of transmissibility. And this is also a powerful principle, which, by the way, you already know, but you don't know that you know. What is the principle of transmissibility? Well, the principle of transmissibility says that I can take any force and move it along the line of action, and the moment effect is going to be the same with respect to the same point, of course. And how do I say that you know that? Because if you realize I can move that force now and put it here, but the distance is always this distance, the perpendicular distance. The perpendicular distance is the same no matter how, if I move the force along the line of action. Now what this is important is that now it's really obvious that if I push it, the effect is going to be like that. And that, according to my convention, is also positive, so I'm going to add that thing over there. Now I take this plus this, and I get my answer, which is the same answer as before. Any question? Like if you can tell me. Well, you send me questions sometimes and I reply those questions. And this is the point where my students say, oh, you are wrong. Why? You're missing the units. And I say, oops, sorry, you got me. Remember, the units are really important, really important. How are we going to solve these problems all the time? You're going to decompose each one of the forces in x and y, and we're going to multiply vertical force times horizontal distance, horizontal force times vertical distance. And I'm going to select one direction for rotation, positive or negative, and I'm going to study the sign and add the values algebraically. And that's basically it. Now, this is the moment that is caused by that force. However, I know you didn't remember the first guy, Archimedes, maybe some of you. I know definitely you didn't remember Varignon, but please make me proud. Let's see if you can recognize this guy here. You remember this guy here? What is the name of this guy? What is the name of this guy? Clue. Isaac Newton. Yes, very good, guys, finally. So this is like the action and reaction, right? The third law. For every action there is an equal and opposite reaction. So basically the moment produced by that force is the one that we calculated. But why this thing doesn't fall, sink, rotate? Because there is something here that avoid that from happening or prevent that from happening. And I'm going to show you just a couple of things here. It's real life, but you have to start wrapping your mind around those things. So basically, if this is what is happening, somehow I have to provide a moment in the other direction for that not to happen. Now, if this is pushing it down, I have to have a force going up. If this is pulling in this direction, the force, I have to have something restraining in that direction also. And this moment that is caused, I have to prevent it. But how do I apply a moment? Basically by putting a force up and down in these bolts. Now, with those reactions, because this is the name of these forces, these are the actions and these are the reactions. For those reactions that we are having here, then you calculate the internal forces, and with those internal forces you generate the shear and moment diagram, which is what we're going to be covering later. And with those internal forces you can calculate the nails, the spacing, the diameter, if those are nails, the section of the wood, how much by how much, 2 by 4, 4 by 8, I don't know, 4 by 6, whatever it is, the material that you need here also. If this is a steel instead of wood, okay, how much is the steel section, the bolts that you have to put here, or the welds that you have to put there. If it's concrete section, the same thing. If it's concrete, reinforced concrete, then the rebars, where the rebars go, the stirrups, the bolts, the foundation, etc., etc., etc. So you really have to learn how to calculate that. And I'm talking about that, but this doesn't have to be civil engineering. Aerospace engineering, same thing. You have to calculate the thickness, the area of the material, the type of material. If the material has holes, those are going to produce internal stress concentration, and all of those are calculated using the internal forces in that material. So look at those bolts, for example. Of course, those are not from this example because this is a theoretical example, but if these bolts were somewhere to be found here in this part, look, what happened in that bolt is that when this was pushed in this way, for this not to fall in this way, basically this bolt here was holding it in place, and that bolt stretched, and the stretching of that bolt could cause this type of failure. You see the stretching there? Now this other bolt will compress, and maybe it will exhibit that type of behavior. Now what happened here? And people say, oh, what happened there is that this came out of the concrete. Well, I didn't say it was concrete, but yes. But why this came out of the concrete? Well, maybe because the adherence wasn't good here. Maybe the adherence, yes, this adherence between this material and that material, but definitely, yeah, that got pulled out of the base. I don't know where is the base. Now with the vertical reactions and this moment also, you can see how the soil here internally behave, and you can calculate that base plate over there also in that part. You can calculate also this with this force here. You can calculate also the bolts, because those bolts, once they are subject to this force, they might try to shear. You see this bolt here, if this get pushed in this direction, the bolt might can fail in that way over there. Or maybe if I push this in this direction, this part here can break, because this part is going to be in tension, the other part is going to be in compression over there. And why not? I mean, you have bolts, you have stresses, you have forces, and believe it or not, the procedure for designing this or for analyzing this is fairly similar to this one. If you want to see something that you have seen everywhere and you want to see it now based on what we are doing here, look at that. Basically the same example that we have here, the bus stop. There you go. Another one. Another one. Another one. What is that? Guess. You know what is that? The death ray? Never heard that before also. Yeah, this is actually an antenna for a ham radio in Italy. That actually existed. Look at that. This is not South Carolina or North Carolina, okay? This is Ukraine. That was built in Ukraine. This is the floating castle, they call it, and there's not such a thing like a castle, but apparently it was something for fertilizing, and that was built in that way only for accessing the trucks here. I don't know, but if you see, it's basically the same principle, one thing and one thing like that. Traffic lights, very similar. This is very complex, but as a very crude approximation, we might try to do an analysis like that if we want to. Okay, fundamental quiz. Let's see if you got this part. If F equals P equals 100, F equals P equals 100, okay, then the moment of F with respect to A and the moment of P with respect to A are equal in magnitude but opposite in direction, or zero. Okay, What do you think? And in class I go, who say A, who say B, who say C, and people say, oh, equal in magnitude but opposite in direction. No, because if I say, look, what is the moment of the force? Force times distance. What is the rotation? If we only study this one, rotation goes clockwise. Now, what is the moment of this force with respect to that point? Force times distance. Same force, same distance. What is the rotation? If I push it in this way, it's going to come in this way. What is that? Clockwise. So the answer should be equal. And then I do another fundamental quiz, which is this one. And I say if F equals P equals 100, is the object in equilibrium? Yes, no. I have not a freaking clue. So, and I make the students to debate. You can think and say, yeah, it's in equilibrium. Well, if it was in equilibrium, then should it be spinning? And that is spinning like that. So it's not in equilibrium. And that links us to the next chapter, which is exactly rigid body equilibrium. When you have particle equilibrium, yes, the amount of unknowns no. When you have rigid body equilibrium, particle equilibrium, the only way that little particle could move was translation. Now, if you have something like this, it can also rotate in different directions. So it's not sufficient now to have summation of forces equals 0, but we should have also summation of moments equals 0. And that's going to be the next chapter that we're going to be covering. But for today, I'm going to stop it here. And I'm going to start this for the next lecture, because this lecture is already 46 minutes long. And I know you get bored with so long lectures, but I'm going to record another lecture only in this part. Okay? See you next time, guys.